Okay, good morning. So we're going to do a little bit less than 1 hour now, and then we take a few minutes break and we do the test.
Can I ask a question?
Yes.
I saw some here.
Okay.
For instance, here the bond structure for germanium. Here we have how do we feel such kind of?
Okay. So your question is about the band structure of silicon, germanium, gallium arsenide as examples. Okay. I think this is a good starting point for a discussion. I would like to start next lecture, because next lecture we're going to discuss semiconductors. So I'm going to start. I had other plans, but we could start from this picture, and then we can discuss semiconductors starting from this picture. Okay? Good. So it's going to be done. When's next lecture, by the way? It's on Tuesday, I think, right? No, I think next week is going to be, well, we'll find out.
Monday morning?
Okay, I might have a problem Monday morning.
So it's the physics.
Yes, that's right. So I might have a problem Monday morning. The next one is Tuesday, right?
The next one is Tuesday.
Tuesday, okay. So we might have to do on Tuesday, not on Monday. I'll let you know. Okay. I need to continue the discussion on transport. Let me again summarize what we're doing here. We have, before I get to transport, we have seen how to construct band structures, what they look like and what they are, what they mean. So this energy versus K. And we use that band structure to classify solids in different categories, primarily into insulators and metals, depending on whether the Fermi level was crossing the bands or not, okay? Whether there was a gap of excitations or not in the system. When we discussed insulators, we essentially looked at the optical properties, just because it's not because metals don't have any optical properties, but because it's more interesting to look at insulators. So our discussion was on optical property was essentially focused on insulators. On the other hand, we are now looking at metals, at systems with zero gap, and so I'm taking this opportunity to study transport, because to discuss transport, because transport is the most relevant property of a metal, of a system where the Fermi energy crosses one of the bands. But this is not, of course, to say that transport is not relevant for insulators and optical properties are not relevant for metals. I'm just using these two categories of solids to highlight some interesting properties of solids. Okay, so transport. Let me summarize briefly what we discussed in class last time. So we have an example of a band. We selected a given K point, a particular K point, and we asked the question, how is an electron filling a state with a particular K in a particular band? How is it going to be affected by the presence of an external field? So we assume that the electron was feeling a force, which is given by the external electric field, and that's the force acting on our particular electron. All right? And through some approximations, it was a very qualitative discussion, I guess. In fact, we explicitly mentioned that this is a discussion that is based on a semi-classical approximation. We came out with the conclusion that the electrons change as a consequence of under the influence of an external field. Okay, they change their state in such a way that the rate of change of their K is equal to minus E. Now we're doing it in 1 dimension. I need your help here. This is over h bar, right? Is that correct? Right. Good. So the rate of change of our quantum number K, so the electrons change their K in a continuous way, and they change their K with a rate which is determined by the external field. And what we notice is that this is a constant rate. The change of k with respect to time is a constant, at least as long as the electric field is a constant. It's a constant field, which means that the electrons essentially change their k with a rate which has a constant velocity in k space, in our space of our quantum number k. All right? So an electron here will move. Of course, when it gets to the edge here, it will re-enter on this side. And as a function of time, it will essentially move periodically through this band over and over and over in a periodic way, under the influence of an external field. Now, what if we have more than one electron? We want to discuss not just one electron, but we want to discuss the properties of a metal, for example. So a system in which we have a Fermi energy, and we have a given number of states here, all filled, and all the other ones are empty. Of course, we're interested only in the behavior of the electrons, right? So the states that are filled, not the states that are empty. This dynamics is the dynamics that will affect the properties of our system for where the electrons are, not, of course, for states that don't contain any electron. Now, an interesting aspect, property of this equation is that this equation does not depend on k. So an electron sitting here and an electron sitting here will move with exactly the same speed in k space, right? So this one will move in k space with a speed which is identical to the speed of the electron here, because the speed is independent. The speed in k space. Remember, this is a quantum number, so what we're talking about is simply the rate of change of a quantum number. And this rate of change is the same. Now, this is somewhat fortunate, because it means that if you have a continuum of electronic states which are filled, they don't hit against each other. If one is moving, because there is an electric field, all the other ones are also moving with the same speed. Right? So there's no problem with, say, filling, say, if this electron wants to move, clearly it wouldn't be able to move to another state because the other state would be filled, in principle, if this electron only was moving. If all these states are filled, an electron sitting here under the influence of an electric field would have to change the k, but the other k is filled. So how can that electron fill a state which is already filled? That is fortunately not the case, because also the other electron is going to be moving with the same rate of change, right? So they all follow like a train, right? They all move with the same speed like a train throughout k space. In fact, like a snake. I like to say that this is like a snake, right? It's like think of it as something that just moves like a snake in the Brillouin zone along the band structure, right? After a given time, these electrons will be here. After another time, they will be here, and then they will be here, and then after a while, they will actually go back to the original position, right? At different times, they will just move around with a constant speed, like a rigid, like a rope. Like a snake that just follows this curve continuously. Now, you might actually ask yourself, how much time does it take for this snake to go back to the original distribution? Well, it's the time it takes to do a full, Brillouin zone, right? If this is the rate of change, well, it is essentially the time it takes to do to run for an amount of delta of k, which is 2 pi over a, in one dimensions at least. Right? So you have at 2 pi over a, the total delta k over tau, the time it takes to go back to the original position must be equal to this rate. well, I mean, the other way to see it is to say that k is equal to minus e times t plus, of course, k is 0, right? So the time it takes to go back to, for k, to change by 2 pi over a is, of course, given by this equality. Right? So tau, we can extract it from here, is going to be, well, let's talk about the modulus, right? The total time it takes. It's 2 pi h bar over E and the electric field. So the stronger the electric field, the shorter is the time, of course, right? So it's because it's faster. Now, yes?
Okay, if the strength of the electric field is large,
Yep.
then I think we would have another correction, right?
Yes, okay.
So,
If the field is too large, there are a number of approximations that we've done in order to get to this point that are not going to be valid any longer. The main one, I would say, is that it is no longer true that you can assume that that the electrons will jump only to nearby states. They will start to jump also across bands. So there will be a possibility for an electron to jump across a band to another one due to the strong electric field. Okay, so you may have other phenomena, nonlinear phenomena. So I'm still assuming that the electric field is small enough that we can still treat the problem as a perturbation theory. All right, so in principle, if we believe in this theory, the electron should be moving with, like snakes here, with the period of given by the external electric field. Now, let's try and calculate now what is the current carried by electrons moving in this way. I mean, so far we've only looked at how the electrons change their state, but we want to calculate the current that is actually carried by electrons. At the end of the day, if we have an electric field, we expect that there will be some current carried, right? And actually our goal in principle is to calculate the conductivity, that is the constant that connects the current to the electric field, right? So that's actually typically the purpose of these kind of approaches. You want to determine how much your system is conductive, that is, what is the constant proportionality between the electric field and the current that you measure in your system. This is Ohm's law, right? It's just, so in principle, this is our goal. Try to see if we can get something like this and possibly also obtain the value of sigma. But let's now calculate what is the current carried by our system. Well, the current carried by your system will be the sum of all the velocities carried by all the electrons that are moving here. Right? So we have to integrate over all the decays. Of course, we only have to consider occupied states. So we have to carry out an integral over k, only, of course, selecting the occupied states, because the states that are not occupied are not carrying any current, of course. Well, then there will be the charge of the electron, of course, and there will be the velocity of the electron at a given k. Remember, each electron here has a different velocity, and we calculated that velocity, remember, last time. So electron here has a velocity which is given by the slope of the energy versus k curve. So we are in a position, we have all the background information to be able to calculate the total current of our system. We just need to take the integral over all the occupied states of the charge, of course, times the velocity of each carrier. Let me forget about normalizations for the time being. I mean, there will, of course, be some normalizations, the volume, and so on and so forth, depending if I'm considering the current, say, the flux of current or whether I'm considering just the current. I mean, there are some normalization factors in front here. But the main point here is that the current will be determined by the sum over all the velocities of all the electrons of my system. Of course, of the electrons existing, filling states in my systems, not of the empty ones. So let me actually make a few, before I go back to this, let me actually make a few considerations regarding this expression here. Suppose, first consideration, suppose that we are at equilibrium. There is no electric field. So the distribution is the original one, this original distribution with the Fermi energy. Everything is at equilibrium. Can I say something about the value of this integral? So one, we are at equilibrium. So epsilon, the field is equal to 0. Can we say something about this J? There's something we certainly can say, and this is the fact that if we are at equilibrium, for every state at a given k, there is a field state at minus k, right? But state at k and states at minus k, if you remember the discussion two lectures ago, they have opposite velocities because everything is symmetric here. So the slope here has to be exactly identical to, well, with the opposite sign to the slope of the curve, to the derivative of the curve at minus k. It might help to remind what the velocity is. And I need your help now. It's 1 over h, the gradient k of E of k, of course. And I'm writing it in 3 dimensions, but of course here we're using 1 over h bar, right? Okay, good. Right, so in 1 dimension is the derivative of the energy with respect to k. So if I'm summing over all the states, and I'm including a state at k, there will also be a state at minus k. If I'm at equilibrium, notice if I'm at equilibrium, because if I'm here, for example, I've clearly, there is no equilibrium, and therefore if I have a state at k, I don't have any state at minus k. So here the situation is going to be different. But if I am at equilibrium, 0 electric field, nothing moves, I can certainly say that J is equal to 0. Okay, I could have probably argued in a different, in a simpler way, but certainly it's comforting to know that this equation is compatible with the fact that J is equal to 0 at equilibrium, just because of this k minus k relationship. Let me make another remark, again, not explicitly connected to this, but it's a very important one. Suppose that instead of having a metal, I have a completely filled band. Okay? So I have all the states are filled. I apply an electric field now, so I'm not putting any constraint on the electric field. It can be finite. The snake, which is actually, I mean, an infinite line, there's no end, right? Because if the band is completely filled, this is a full snake. I mean, it's a snake that continues all over. I mean, fills all the states. This will move uniformly, but at the end of the day, all the states will be just filled. There will be no change in the occupation of the states. The electrons will move, right? The electrons will jump continuously from one state to another one, but as soon as one electron jumps, there will be another electron that jumps on the same state. So as a matter of fact, when I calculate this sum here, this sum will not change with time, because it will be just the sum of all the states will be occupied. So I just have to take this integral over the full band. But again, if I'm integrating over the full band, I have states at k and states at minus k, right? So as a result, J also must be 0, right? Notice that this is valid regardless of the value of electric field. So I'm talking about this is a result that holds even when the electric field is finite, because everything moves, but all the electrons will move, but the occupation will be exactly the same as a function of time. All the states will be occupied. And when I carry out this integral over all the states, for a given k, I have a minus k, so that sum is going to be 0. Right? So this is another very strong statement, actually less obvious than this one, because what I'm saying is that if the band is completely filled, it carries no current. Of course, we are in the limit of perturbation theory. If you go beyond that, there will be some finite current. But in the limit, perturbation theory is correct. That is, there are no transition between bands. The completely filled band, whatever is the electric field, carries no current. So this is actually a strong statement because it says that in an insulator, where all the bands are filled, there are no half-filled bands, the current must be 0. There's no current flowing in an insulator, right? Because all the bands are filled, and each one of them carries no current. Okay, so there's no net flow of charge. The electrons move, by the way, again. They're not static. They're not at equilibrium. They move, but every time an electron moves, there will be another electron filling the same state, so the total contribution to the conductivity, to the current is the same. So the current doesn't change, and it is 0. There is another interesting property which I will mention now, and I will come back to this in 1 or 2 lectures. And this is the following. If I have now a partially filled band, like this one, so let me go back to this situation now. There's another important, interesting statement that I can make. Again, I'm assuming that the electric field is finite. I can think of, let me construct this current, this object J, as, sorry, let me start from here. So let me assume that we have a completely filled band. The total current is 0. No, I have to do it here. Sorry. Okay. I can write the following J, which is this integral over occupied states of our dk minus EVK plus the sum over empty states. This is just I mean, that's nothing physical. I'm just constructing an object, okay, and I define it. Let me call it like this. The J tot of a given band has no physical meaning, but I construct it as the sum of the current carried by the occupied state and of something that doesn't exist, but I call it the current carried by the empty states. Of course, there's no physical meaning to that. There's no current that the empty states can carry because the empty states are empty, so there's no current. But suppose I construct this object, mathematically speaking, that is, I carry out the integral over the occupied state, and I sum to the integral over the empty states. Now, the sum of these two terms has to be the integral over the whole Brillouin zone of minus EVK. Right? Because if I sum over the occupied states plus the sum of the empty states, I'm actually summing over all the states. But the sum over all the states is exactly 0.2. It's the same quantity I calculated when I calculated the current carried by the completely filled band. K minus K, this is 0. So what I can conclude is that the current actually carried by the system, by the real electrons, by the occupied state, it is equal to minus the current carried by the empty states. Now, again, empty states don't have any physical meaning. But from a mathematical point of view, I can say that if the empty states were carrying charge and the occupied states were not, let's imagine a world in which the empty states carry charge, carry current, and the occupied states that don't, I can say that the current carried by the empty states is equal and opposite to the current carried by the occupied state for a given band, right? Because the sum of the two must be 0. Okay? Now, the reason I'm mentioning this is not because empty states carry any current, of course, from a physical point of view, but because there may be situations, and we'll see one in a lecture, in a couple of lectures, in which it might be much easier to calculate the current assuming that it's the empty states that carry the current. Because it's easier to carry out this integral than to carry out this integral. Okay? So it's better for us to think that current is carried by empty states rather than it is carried by occupied states. Of course, we always have to keep in mind that physically speaking, it's the occupied states that carry the current. But through this special relationship, to the fact that the occupied states carry a current which is opposite to the current, hypothetical current carried by the empty states, from a mathematical point of view, if it's more convenient for us to calculate this integral rather than this one, it's better to do it like this, to think in terms of current carried by empty states. Those of you who are familiar a little bit with solid-state physics might start to realize that this is exactly the concept of holes. That's exactly the reason why in solid-state physics the concept of hole is so important. Holes are electron vacancies. That is missing electrons. So of course holes don't have any physical meaning because they're not real particles. They're just whatever is missing, I mean empty states. But there are situations in which it might be better for us to think in terms of empty states rather than to think in terms of occupied states. And this relationship is the reason why the two, I mean, we can look at the current in both ways. One is the opposite of the other. Okay? So, in partially filled band, finite electric field, I can say that the current carried by occupied states is equal to minus the current, the hypothetical current carried by the empty states. Of course, always keep in mind that the only physical current is the one carried by the occupied states, of course, because these are the electrons, the real particles.
Sir,
Yes?
if the charge minus E for the empty one,
Yeah. Why not? It's minus, right. I'm saying, suppose that it's the empty states that carry the current. With this charge minus C, of course. Otherwise, I'm not able to say that this is equal to 0, right? If I put plus here, I won't be able to claim that this is equal to 0.
Maybe you can say the charge is...
Right. Okay. Then I can say, let's give it a charge of plus E to the empty states, and then the two currents are the same. We'll do that. But for the time being, let's just keep this in mind. This is the only thing we need to remember at this point of the discussion. Yes.
When we have an electric field,
Yes.
and, in the situation when it's partially
Field.
by symmetry, we have another situation when we have.
Oh, yes. So you mean this one here? Okay. So you're asking if we have an electric field in a partially filled band, which is this one. There is another situation, which is exactly this one. Yes, correct. This one here. Or if you wish, this plus this, right? Depends how you look at it. In which K and minus K cancel, and the current is 0. So the answer to this question is yes, there will be a time in which the current is again 0. In fact, let me try to imagine what the current could look like here. Let me keep this time because this will be important in a second. So if I try to imagine now, as a function of time, how my current could look like for my system. Suppose I start from equilibrium, okay? The current is 0. I switch on the electric field. The snake will start moving. Actually, we'll start moving in the opposite direction because dk is minus E, but whatever, I can change the sign of the electric field. It's okay. Let's suppose that it's moving in this direction. Now, if it's here, clearly the slope is positive, right? So the velocity is positive, everything is positive. Well, minus C, it's okay, I'll go down like this. There will be a point in which this is maximum, right? Because at some point it will have to go back to 0. Well, it will be something like that. It will go through 0 when it's here, and then after a while it will go back to 0 because it goes back to the original position, right? And we calculated the time it takes to go from here to here. This is this period. And then, of course, it will just continue forever. Up and down, up and down. And the shape of this curve will depend on the shape of the band structure, because the velocity is the derivative of the band structure. But certainly what we can say is that this is going to be an oscillating function, periodic, with periodicity given by this number. So what do we have at this point? We have an electric field moving the electrons, causing a current this time, right? It's not that the current is 0, so it's not in the trivial case. We have a current. The current is time dependent. It is periodic. The average of this current is 0, right? It's easy to imagine it's 0 because this is a snake that is going to run throughout the band structure. And we know that the average current carried by band structure is 0. We've done it several times here, right? So the average in time, in the time domain of this current, if I take the average in the time domain of this current, this is going to be 0. So we have an oscillating current whose average is 0. Now, I guess you all realize that there is something wrong here, right? We have an electric field. It's fine that we find that the current is 0 for an insulator. It's fine that we find that the occupied state is minus the holes. I mean, this is something you probably remember. But finding that the current carried by what is clearly a metal is 0 under an electric field is not something that we like, right? There's something wrong in this argument. So, in order to understand what's wrong in this argument, I think it's the best thing to start, it's the best thing to do is to try and evaluate what is the period of this oscillation. I don't want to enter into discussion about the strength of electric fields. I just want to say that for standard electric fields, the typical period of oscillation of this is of the order of 10 to the minus 10 seconds. All right? Of the order of, can be 10 to the minus 9, 10 to the minus 11, 10 to the minus 8, depending on the strength of the electric field. For standard fields in the volts regime, this period of oscillation is of the order of 10 to the minus 10 seconds, even less than that, depending on the strength of the electric field.
How much is the standard strength of electric field?
I'm thinking of standard electric fields of the order of volts over, say, millimeters or over centimeters. Okay, the standard field that we have in a circuit, for example, in electric circuit. So it takes a pretty long time to do this. Well, 10 to the minus 10 is not that long. It's not that long. It's quite short. But on the time scale of electrons, it is actually very long, fortunately. What happens in the real system? Let me re-plot this energy band now. Energy band, we start from where's the pink? We start from the pink distribution. We switch on the electric field. After an infinitesimal amount of time, our snake will, I will now do it with a different line, will be like this, right? It will have moved by an infinitesimal amount on the left side and infinitesimal amount on the right side. Now, this is after an infinitesimal small amount of time, or at least much smaller amount of time than the period. Now, clearly the system, the electronic system now, is out of equilibrium. So the real question we need to ask at this point is whether in this amount of time, which we assume to be much smaller than the period of the oscillation, there are chances that the system finds a way to re-equilibrate, to go back to the equilibrium state. Right? Certainly, if this electron, for example, or all the electrons that have exceeded what was originally the Fermi level, will find a way to go back here, for example, then we would re-equilibrate the system. We would bring the system back to equilibrium. Notice that in order to do that, we are not forced to push the snake back rigidly. We can just take electrons, the electrons that are spilling out from this side, and sending them back to the other side. If we have a mechanism that does that, any mechanism, the system will, of course, take advantage of that mechanism because it's a way to re-equilibrate the system, to lower the energy, clearly. Right? Because clearly a situation in which the snake is out of equilibrium is something that cannot be sustained in the long term. It's not a ground state of the system. So any mechanism, it could be scattering with impurities, it could be scattering between electrons, it could be anything. Any mechanism that pushes the system back to equilibrium is going to send electrons from here back to here and try to re-equilibrate the system. So there is clearly a competition here in this story between the electric field that is pushing the electrons away from equilibrium in this snake-like fashion, very nice but completely realistic fashion, and any other mechanism that tends to bring the system back to equilibrium, to the ground state. And there are several, fortunately. There is, for example, scattering with impurities. With impurities, it's almost impossible to prepare a metal which is totally free of impurities. There will be impurities. Impurities are there. Impurities perturb the motion of electrons, and as any other perturbation, they clearly will contribute to equilibrate, to thermalize the system. It's like, adding some system that some external perturbance that can thermalize the system more efficiently. There would be scattering of the electrons between themselves. Okay. Here we are assuming that the electrons don't see each other in our theory, but electrons actually see each other because there are Coulomb interactions between them, which we are completely forgetting in our, or at least we are treating only in an effective way in our theory once we consider the band structure formalism. And then there are scattering with phonons. We didn't discuss phonons yet, but phonons are the perturbation, the deviations of the nuclei from the ideal crystal positions due to the finite temperature. We're going to discuss them in a couple of lectures. So departures from the ideal crystal configuration, which is what allowed us to build the band structure, will be additional reasons why the electrons tend to go back to the ground state. So there are a number of mechanisms through which the electrons can find a way to equilibrate back to the ground state, to what is their ground state. So the whole thing is a competition between processes that would tend to send the electrons back to equilibrium and the electric field, which is trying to push the system away from equilibrium. All right? Now, as a matter of fact, the time it takes for an electron here to be scattered back to equilibrium is actually extremely fast. The probability that an electron is scattered back to a state with lower energy as soon as the system is brought out of equilibrium is extremely fast. So let me group these phenomena all into a single scattering time, which I call actually tau s. So let me assume that I can simplify all this discussion into a single scattering time. There will be an average time after which an electron will decay back to the state with lower energy. What we know is that these scattering times are typically much, much faster, much lower than the period of oscillation due to the electric field alone. Okay? So the probability that an electron will be scattered back to a state with lower energy is extremely high. As soon as the snake starts to move, it will be immediately be pushed back to equilibrium by these scattering processes. The probability that these events take place is very high. They take place with a rate which is much larger than the rate than the period of oscillation of the electrons, according to our theory of these snakes moving around the Brillouin zone. So we can actually conclude that this system will reach an equilibrium, okay, a dynamical equilibrium, in which the snake will have moved by only a little away from equilibrium, and that little is actually determined by the speed at which it is sent back. Right? So if I want to calculate this delta k, how can I estimate it? Well, this delta k, in a time after I run a given delta k, after a time tau s, I will be scattered back to the original, to the state with lower energy. Okay? So after a time tau s, my electron will have moved by an amount delta k given by, where is it? EH, well, forget about the minus here because it's we're talking about absolute numbers. So the amount delta k by which an electron will have moved before it is scattered is going to be given by this relationship. Right? So there will be an imbalance in our distribution, right, which will be given by delta k given by this relationship. So the overall delta k, let me write it here, will be tau s. That's the imbalance of our distribution. Yes?
When the system is in equilibrium,
Yep.
we assume that these mechanisms are not there.
No, they're always there because you have to think at a snake that is continuously moving, right? And as soon as it moves, you cut the head and you bring it back to the tail. But the snake is continuously moving. The electron will be jumping, pum, 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 until they get to this point. And once they get to this point, they are scattered back here. Okay, so the snake is continuously moving, but you are recycling whatever exceeds the Fermi energy in a very short time, because this time is very short, the time it takes for an electron to realize that you're above the Fermi energy and you have to suddenly go back to below the Fermi energy. All right? So the system, it's actually a dynamic equilibrium. Okay, the electrons are actually moving here with this speed, all right? But as soon as they get to this point, they are scattered back to a state of lower energy. As soon as they realize that there is a state of lower energy that they can access, which means as soon as they cross the Fermi level, boom, they will be sent back immediately through these processes back to the state of lower energy. So the amount of delta k that will give the imbalance is going to be given by this expression. And it is precisely this imbalance that is going to give us the final current. Because all the other states, k minus k, they cancel. It's only states here and actually also here, because I don't have to forget that I also push the distribution to the right here. So there are imbalances here and here. Actually, they are both on this side from a physical point of view. There are states here and states here that don't have any, say, analog on the other side. right? There's an empty state on the other side. So all the states below this point have an analog, so it is k minus k, but there is these two ranges of k, actually twice delta k, therefore, that is not balanced by a state at minus k. So it's only these states that contribute to the current. So out of this integral over the occupied states, I only have to pick up these states. All the other ones I know they're not going to contribute. Yes. Is there a question? Yes.
Is there a model that this process?
Is there an electric? No, I already told you that any for typical values of electric fields, this tau is very large. So the process is the period is very long compared to this period. So for me at this point, the only condition I need to consider is that this is much smaller than tau for this theory to apply. No, because at some point, if the electric field is too large, this tau becomes too small, and this condition does not hold any longer, okay? That is, or equivalently, the equilibrium would be a distribution which is very far from the equilibrium, right? It's very shifted from the equilibrium. We know that this is not something we accept, because that means that we are in a non-perturbative regime. Okay, so you want to know what is the threshold in electric field in typical terms. I would say it's of the order of kilovolts per millimeters per centimeters. This is the typical fields above which you have to consider a number of other effects. The conductivity is typically non-linear. You start having transitions between bands. So you have to really be applying strong fields, like of the order of, say, above 1,000 volts per, say, millimeter or centimeter, standard thickness of a sample. Okay? Otherwise, you are surely in these conditions. And if you're in these conditions, we can apply this perturbative theory, and we can discuss the problem in these terms.
So we have to know the value of the range of TS.
Yeah, of course, yes. We have to know TS, right. The typical values of TS are always in the range of 10 to the minus 13, 14 seconds. Typical values of the scattering times. Okay, for typical solids, typical metals. They're very efficient. Of course, they will depend on temperature, because scattering by phonons, for example, will be determined by how hot the system is. The hotter is the system, the faster will be the scattering times. Depends on the amount of impurities that you have in a system. If a very pure system, the scattering time is going to be longer, if the one due to impurity. So it really depends on the system. But more or less, we are talking about something which is a few orders of magnitude smaller than the period that we would extract out of this very, very simple and naive theory. Yes? This 10 to the minus 13 is much smaller than 10 to the minus 10.
Okay.
No?
I don't know. Maybe.
Why?
It's just like 10 raised to minus 3.
Yeah, 10 to the minus 3 is a lot. I mean, it's much, much smaller than, yeah. In any case, I mean, even if it's 10 to the minus 1, we could still say that this is the dominant contribution in theory. We don't want to build an exact theory of transport. I just want to give you a qualitative.
We say tau can range between 10 raised to minus 7
No,
and
okay.
minus 11.
There are, well, the point is that if as soon as you increase the electric field, all your theory breaks down, essentially. Okay? So in the range of values of electric fields for which our theory is valid, this condition is actually satisfied. Okay, so then we have to calculate the current, and this current now is the one carried by these states here. Well, so it's essentially just minus E The velocity here will be the velocity at the Fermi level, right? Whatever it is, it's the slope of the band at the Fermi level. And the integral here, I can just replace it by the values of delta K that contribute to the current. Right? I have to carry out this integral. I know this integral is going to be compensated for all values of K with exception of this range here. Well, there's actually a 2, if I want to be precise. Yes, because there's 2, there's K and minus K, or twice the K. Right? So let me say, in terms of, without, really talking about the constants here, we have E squared over H bar VF tau S. Sorry, I should have used this one. E squared, and right? And the factor of 2, of course. You can put the factor of 2 here if you wish. But it's not really relevant. So the important thing here is that now, finally, we've obtained something that depends linearly on the electric field. So this is what is our conductivity now. Sorry? It must be positive. If it's negative, it's because of, let's see, I think it's because I should have considered that the current is moving in the opposite, because if I apply an positive electric field, actually the electrons move in the opposite direction. Remember, it was minus K, delta K over delta T is minus E times the electric field, right? So for a positive electric field, the electrons actually move in this direction. So everything should have been reverted. So this snake actually moves in the opposite direction. I think, let's forget about the signs. It's certainly going to be positive. Whatever it is, it must go in the direction of the electric field. If you want to do it precisely, then you have to consider that this actually is moving in the opposite direction. So you have the current carried by states here, so the current is actually positive, because the velocity here is the opposite of the velocity there. All right, so to finish this, we have that the conductivity of a system is proportional to the velocity of the electrons at the Fermi energy. The velocity of the electrons elsewhere is irrelevant because they're not contributing to the current, because elsewhere they are compensated, K minus K. So only the ones at the Fermi level contribute. And it is proportional to the scattering time. Okay? Of course, I'm oversimplifying the discussion here because I'm assuming that there is a single scattering time. In fact, there may be many scattering times, and the scattering times may depend on where I am on the Fermi surface and so on and so forth. But here, for a simplified discussion, I can assume there is just one scattering time. It's for us to understand the physics of the problem. And the conductivity is proportional to the scattering time. So the faster is the scattering time, which means the stronger is the scattering with whatever impurities, the more impurities we have, right? The shorter will be the scattering time, the lower will be the conductivity. So it's all natural now that we think about it. If I have more scattering phenomena, more scattering events, my electrons will have difficulties moving, right? And this is reflected in the lower scattering time, faster scattering. And if the scattering time is low, of course, the conductivity will also be low. Okay, so the electrons have difficulties moving because every time they try to move here, they are scattered back very efficiently to the equilibrium. Okay, I think it's the perfect place where to stop. Is there any question at this point? Yes. Sorry? Oh, what about temperature? Okay, temperature here enters in determining particularly this one, I would say, because temperature is not really affecting the scattering with impurities, not, too much at least. marginally is affecting scattering with electrons. It is certainly affecting scattering with phonons, because at low temperature, the solid, the nuclei will be at the ideal positions. At high temperature, they will be vibrating, and we will examine these properties later on. But I guess you might be obviously familiar with the fact that whenever you're at finite temperature, there will be departures of the nuclear positions from the ideal crystal positions due to finite temperature. So you might expect that scattering with phonons grows with increasing temperature, and therefore the scattering time due to scattering with phonons will become lower and lower with increasing temperature, right? Faster and faster to be scattered with phonons, because there are more phonons, more vibrations, more disorder in the system. Okay, so it's scattering by phonons is faster, and therefore the conductivity becomes lower and lower and lower. Okay, so the simple minded picture of this is that if you increase temperature, mostly because of the scattering with phonons, the conductivity will decrease. Or, if you wish, the resistivity will increase, which is what we know from, say, probably high school. That if you increase temperature, the resistivity of a metal increases. It becomes more difficult to conduct current when you increase temperature. And this is primarily due to scattering with phonon. The fact that the phonon scattering becomes more efficient because there are, the system, the underlying lattice becomes more disordered, so it gives more channels for the electrons to decay back to equilibrium. Yes? It's what, sorry? The time it takes for electrons to go from here to here, yes? No, it's given by, it's the scattering time, right? So the time it takes to go from here to here is the scattering time. There should be what? Sorry, can you speak? Now, think of this as, again, as a snake, right? It's moving, so it's moving out of equilibrium. So there are states available here and states above the Fermi level here. So these states are scattered back to the empty states here very efficiently with the scattering time, which is very fast.
Everything is moving.
Right.
So as it is moving, well, the first one, the time for the first one to go.
Right, to get back.
It should not be directly behind the last one.
Oh, you mean, okay, so, okay. So you are trying to understand, I mean, the problem from a more sophisticated, it's too much sophisticated what you're saying. Okay, so your argument is the following. Suppose that my distribution now goes from here to here, right? You're saying an electron here, where will it go? Will it go exactly here, or will it go somewhere else? Is this what you're asking? Okay, so in principle, it can go anywhere between this point and this point, because all these states have a lower energy than this one. Right? So it can be scattered anyway. If the purpose is to lower the energy, there are several states available that could lower the energy. So your question is, where does it go? Does it go here, or does it go here? Where does it go? Well, as a matter of fact, the scattering within these states is even faster, because they're even closer. So this process is actually instantaneous on the time scale of the scattering from here to here. All right? So it doesn't matter. As soon as the electron jumps on the other side, you can assume that it fell down to the lowest available state. This process is irrelevant for our discussion. Any more questions? Yes?
How much is the energy scale to scatter the electron from that one to here?
Oh, okay. We can calculate it, right? It's, we know delta K, so we just have to calculate. So delta K is E epsilon over H tau S, right? And so this is delta K. Delta E will be the derivative of E with respect to K times delta K. So it's actually H times the velocity at the Fermi level, because that's the derivative with respect to k times delta k. So it's E epsilon tau S over h bar, and h bar disappears here. Okay, so this is the value of the...
Okay, now if this energy is like comparable to the energy gap between the first and second, can it go?
Oh, okay. So you're saying now, if this energy becomes comparable with, you mean with the distance between bands? Yeah, of course, yes. You can actually take, I think, safely this as a criterion to decide whether you are in a perturbative regime or not. This delta E must be much smaller than differences between bands. That's a good point, yes. And that will give you a threshold, a threshold for the value of the electric field for which this theory holds or not. Yes, good point. So he's arguing that this delta E must be much smaller than the distances between bands in order for this theory to be able to neglect transitions between bands. Yeah, that's a good point. No more questions? Okay, so we're done with the lecture, and now we'll go to the other room to do the test.